So we use a TDR for a few different functions, but one of the things that we use it for is to make sure that the measurement system is providing a flat response. We don't want to see ringing from our gallium nitride elements if it's really coming from the scope and the probes. So we want to know what that response looks like. The signal generator here is a 32 picosecond edge, so about a 10 gigahertz bandwidth, and it goes through a power divider here. And in this particular measurement, we're measuring the bandwidth of really a flat wire. And so it's this RG405 rigid coax and the BNC connectors on the end. And you can see that's pretty flat. And so that's what we expect. You might have noticed it's showing 6 dB, and that's because I didn't correct for the 6 dB attenuation of the splitter. But we also use this to measure the probe. So we want to make sure the probe itself is flat. And that's one of the beauties of the power rail probes, is that they are so flat. And so here is the TPR 4000. Let me just reset the averaging. And now you can see that's within about plus or minus 1 dB or so out to 4 gigahertz. And that's a pretty good looking edge. So we won't get ringing from the probe. We could get ringing from the interconnects if we're not careful in the probe tips, but the probe itself is nice and flat. And that's one thing we can use the TDR for. The other thing that we use this TDR for is to check the cables and our printed circuit board traces, including the printed circuit board coupons. So I'm using the same generator, 32 picosecond edge, so 10 gigahertz bandwidth. And the top trace here, we're looking at the voltage generated by the signal. And here's the zero level, here's the plateau, and that plateau is generated by the cable. So that's actually the measurement of the cable. And then this is the end of the cable here. The scope math expressions convert that to reflection coefficients, which go from 0 to from -1 to 1, and a perfect 50 ohm match being 0, and that's the center line. And here we converted it to impedance in the bottom trace, and have a math function that takes the average between the two cursors and displays it here. So this says that our 50 ohm cable is about 50.8 ohms, so that's pretty good. And it's a good idea to check your cables, because we want to make sure that the cable's in good shape before we make measurements. If it's not, usually what we'll see is degradation in these impedance measurements at one edge or the other of the cable, and that's a reflection of how good the crimp is. And once we have the cable, we can also connect it to a probe, which makes it really handy. So this is the new P2104 probe that I'm using here, and I have a couple of different traces that we'll look at. One is just a 50 ohm trace, and so I can just put the probe there, and then you can see here's the 50 ohm line. We can move our cursors, and that'll tell us the impedance of that trace. And you can see that's just a little on the low side at about 48.7. This little glitch here is actually the inductance of the probe, and that's a pretty small one because this is a 14 gigahertz probe, and a lower frequency probe it would be larger. We can also look at traces that aren't quite so ideal. And for example, this one has two little divots in it, one here and one here. And those show up in the impedance, and you can see they also show up in the reflections. And we can use that to tell exactly what the dielectric constant of this printed circuit board is if we know the distance between them. So you can see the distance is marked on this demo board that says those are exactly 3 inches apart, and that'll tell us about how fast the signal travels, and that'll also tell us about the dielectric constant of the board. We can also use it to measure higher frequency traces, and here's a nice high frequency trace here, and we can zoom out on that a bit using the pinch function, which is nice. And now here we can see there's the divot that shows up from the probe tip, and then here's the trace right there, and that tells us that's also about a 50 ohm trace. I made these two circuit boards so they have identical 50 ohm traces in them, but one has a solder mask and one doesn't. And so here again you can see the divot, and now you can see here's the impedance of our short trace, and you can see that's quite a bit lower than 50 ohms. That's actually about 41, and here it is with the solder mask. and including the solder mask, you can see it's quite a bit higher. And so 46 ohms. Make sure we got on there well. Yeah, now we're placed better. That's 48.5 ohms. There's about 2 ohm difference between the two traces because of the solder mask. And so we can use this to quickly characterize the printed circuit boards and traces, and also to make sure that the cables that we're using are intact. There's nothing worse than spending a day making measurements and then have the connector fall off and find out that they're all bad measurements and having to start over.